last day by recalling the definition of the eigenvalues and eigenvectors. And we have this interesting problem in that, typically we're given a matrix A and we have to solve for both the eigenvalues and the eigenvectors. But it's one equation involving two of them. And the way we tackle that problem is we first calculate the eigenvalues as zeros of the characteristic polynomial, as we said at the end of last day's class. And then for each eigenvalue, we compute the eigenvectors. Okay, so just to recall that a square matrix A, we're restricting ourselves to R n by n matrices whose elements are real numbers, although what we're talking about holds for complex numbers, complex A as well. And we say that EI is an eigenvector of the matrix A corresponding to eigenvalue lambda I if this equation is satisfied. All right, so EI is a vector in Cn. And lambda I is a complex number. All right, so in general, you know that even for real matrices, we could have complex eigenvalues and eigenvectors. But we do know that if A is real and it has a complex eigenvalue-eigenvector pair, then it's another eigenvalue-eigenvector pair must be the complex conjugate of those in order that A is a real matrix. Okay, so they must, if you have complex eigenvalues and eigenvectors, they occur in complex conjugate pairs. All right, so that's what we're recalling. And so we take, we take this onto the other side, we solve for EI, and so we're saying, if EI is non-zero, which is the definition of an eigenvector, it's not a zero matrix, then we can solve that equation by first solving for the determinant of lambda I minus A is equal to 0. All right, because it necessarily has to have a non-zero null, non-trivial null space, and that's at, say, lambda I. So we solve for lambda I. And then we solve for the eigenvector, or eigenvectors, by determining what the null space of A minus lambda I, or let's write it in this way, the null space of lambda I minus A. So we're going to solve for that null space. So this is how we compute the eigenvalues lambda I, and that's how we compute the eigenvectors corresponding to eigenvalue lambda I. Okay, so that's a procedure. I think all of you have seen that before. So now let's dive into these two cases. Let's first of all look at this case, and we're going to look at a special, as I said last day, kind of a special case of case 1 first. We're going to start with the case in which you have a matrix A, you've computed those eigenvalues, and they're all distinct. They're all different from each other. Okay, so we're going to look at a subcase of 1, namely A has distinct eigenvalues, evals eigenvalues. All right, so you can still have, complex eigenvalues because, complex conjugate pair, those are two distinct eigenvalues. One's alpha plus j omega, one's alpha minus j omega. They're still distinct, right? Okay, so the subcase we're going to start with is the case in which A has distinct eigenvalues, and we're going to prove in this case that that A has n linearly independent eigenvectors if it has distinct eigenvalues. All right, so that's the first case. That's actually the theorem that we have here. So the theorem is that if A has distinct, let's just be very careful here, has n distinct eigenvalues, then it has n linearly independent eigenvectors. And the way we're going to pose this, or the way it's posed in the statement of the theorem, is we say that the corresponding eigenvectors E1, E2, up to En form a basis for Cn. The vector space Cn over the fields. All right, so we're saying that there are n of them. They span the space Cn, but they're also linearly independent when we say it forms a basis.
When you said subcase of 1, was one of these equations that are 1?
No, this 1 is over here on this board that you probably can't see very well. 1 is the case in which we have n linearly independent eigenvectors. All right. So case 1. So I'm going to just rewrite it over here. This is the good thing about you guys filling in the post-midterm survey. Does anybody need one of those? You do, because I printed off exactly how many of the students there are in class, and there's still a whole pile left here. Good. And the reason is because somebody, thank you for those who filled it out and gave it back to me already, somebody said, you know, I really can't see when you write on that board, or write on that board over there. So I'm going to be a little more careful. I probably still need to use this board, but if I'm over here, you can't really see that. Can you, Henry? Where? Okay. So what's the disappearing line? What if we go like here? Is that okay? If I use these two boards, this board and this part of this board predominantly, is that okay? Is that? Are there any problems? Who else needs a survey? I know some of you do. Okay, and you can just pick them up. I've got, you know, leftovers up here. But I really appreciate, again, if you weren't here on last day's class, it's anonymous. You can put your name on if you want. You don't have to. Hand it back to me or in my box or on my door. I just really like getting this midterm survey feedback because as we're doing today, we can kind of implement some of these things to you know, make the class better for the class. Okay, so so case 1 is the case in which A has n linearly independent eigenvectors, and I've just posed it in another way here. The way the theorem stated in the notes is that, you know, if we talk about n eigenvectors and they form a basis, then we know they're linearly independent. Okay, so we're going to prove this. It's a nice little proof. It's an important theorem, and so the proof of this theorem there's probably a number of different ways you could do it. The way I did it was assume that they're not independent. So those are not linearly independent, and then derive a contradiction with the fact that A has n distinct eigenvalues. All right, so if this set E1, E2, this set of eigenvectors is not linearly, it's not a linearly independent set, then what that means is that you can look at a linear combination of these eigenvectors. So you've got alpha 1 E1 plus alpha 2 E2 plus alpha n En is equal to 0, where at least one of those alpha i's, so those alpha i's are complex numbers, at least one of them is not 0. Alright, so now we know at least one is not 0. So without loss of generality, let's suppose that alpha 1 is not 0. I could have chosen a different one or some combination of them. The proof still holds. So assume, and then WLOG, without loss of generality, that alpha 1 is not equal to 0. And then take this equation here and just pre-multiply that equation by the following product. So I know alpha 1 is not equal to 0, and I'm going to take that equation and multiply by the following, pre-multiply by the product of the following matrices: A minus lambda 2i, A minus lambda 3i, A minus lambda n I. Okay, so I'm going to multiply that by alpha 1 E1 plus alpha 2 E2 plus alpha n. Okay, and that's going to be equal to 0. Okay, so what happens? Well, let's just suppose for this proof, and you'll see how it generalizes, let's just focus on the alpha 1 E1 term, because I know that that's not 0. And let's look at what alpha 1 E1, so I'm going to now look at this last term here, A minus lambda Ni times alpha 1 E1. Well, alpha 1's just a scalar, so it can come back up. I can put it here. E1 is an eigenvector of A corresponding to eigenvalue lambda 1. So when you bring the E1 in, you're going to get A E1 minus lambda n times E1. But A E1, by definition, is lambda 1 E1. And so I'm able to take that expression. So let's just write the next step. So I've still got my matrices up here. A minus lambda 3. I, and then I've got my alpha 1 here. This term here becomes lambda 1, well, let's just write it as a scalar, lambda 1 minus lambda n times E1, and I'm just going to put my E1 back here. Okay, because these are just scalars, so I can change, I'll keep the scalars back here. I can move them wherever I want in this product. And then you keep doing that. So each time now E1 is going to be multiplied by the matrix A minus lambda n minus 1I. And so E1 is an eigenvector, so you're going to get lambda 1 minus lambda n minus 1. Okay, so I brought this back. I'll have additional terms here is equal to 0. Okay, so you just keep working backwards. You just keep jumping, pulling that back. And so eventually what you get is what we have here in the notes, alpha 1, lambda 1 minus lambda 2, lambda 1 minus lambda 3, all the way up to lambda 1 minus lambda n, E1 is equal to 0. Okay, so what I've written here is the case in which alpha 1 is not 0, but the rest are 0. So I've assumed the rest are 0 again. Okay. But let's just continue with that case. So now you see you derive the contradiction, because on the left-hand side, I have all these terms. So E1 is not the 0 vector, and then I have all these scalars which I know are not 0. By assumption, alpha 1 is not 0, but also by assumption, the eigenvalues are distinct. So lambda 1 minus lambda 2 is not 0. Lambda 1 minus lambda 3 is not 0, etc., etc. Okay, so here I derive a contradiction, and I've derived it assuming without loss of generality that it's the alpha 1 that's not 0. You can see now that if I had, any of the alphas not being 0, but also if I had, a combination of these alphas not being 0, you could still use the same method of proof to derive this contradiction. Okay, so this tells us that this contradicts alpha 1 not being equal to 0. So it's a proof by contradiction that a matrix that has distinct eigenvalues has n linearly independent eigenvectors. Okay, so that's sort of a neat fact that you have a square matrix, you compute its eigenvalues. If you know that if you look at those eigenvalues and you see they're all different from each other, you know right away that it's got n linearly independent eigenvectors. We often call that a full set of eigenvectors. The most it can have are n, and it's got n. All right, so we're going to come back to this point because it's important. Well, it really becomes important when we get to case 2, where A has less than n linearly independent eigenvectors. But I'd like to continue and just say, A can have n linearly independent eigenvectors even if it doesn't have distinct eigenvalues. So we also note that we also note that A can have n linearly independent eigenvectors even if it has repeated, I'll put that in quotes, repeated eigenvalues. And that's basically because you may have, for example, well, let's just sort of look at an example here. Suppose you had, well, let's just keep our example that we've been using. Suppose these lambda 1, lambda 2 up to lambda n are the eigenvalues of A, and suppose lambda 1 equals lambda 2. Okay, so it has two eigenvalues at lambda 1. Suppose this is equal to lambda, and that's equal to lambda. So it's got at least two eigenvalues that are the same. That's okay, as long as associated to that eigenvalue at lambda, of which it has two of them, there are two eigenvectors, two linearly independent eigenvectors. So this, what's the right way to say it? So even though A has two eigenvalues at lambda in this example, it can have two linearly independent eigenvectors associated to this eigenvalue at lambda. And the way you would check that is you just say, okay, well, I know it has an eigenvalue at lambda. Let's compute the eigenvector associated to that eigenvalue. So what do? You go back to your algorithm for computing eigenvectors, and you say, all right, well, let's compute the null space of A minus lambda I. Now I'm choosing that lambda to be the specific lambda here. Let's use lambda star just to make sure we're not talking about a generic lambda. Even though it has two eigenvalues at lambda star, it can have two linearly independent eigenvectors associated to that eigenvalue at lambda star. So you plug in lambda star into this equation, into A minus lambda I. So you determine that matrix, A minus lambda star I, and then you compute its null space. And so the null space of this would have to have dimension 2, right? Two-dimensional null space. Okay, so the key thing when we talk about this case 1 is that the matrix has n linearly independent eigenvectors. Because if it has n linearly independent eigenvectors, you can do a lot. You can diagonalize that matrix. Okay, and that's what we're going to see now. All right, so in summary, what we've done today is we've talked about case 1. A has n linearly independent eigenvectors. We've looked at a special case of case 1. That is, if it has distinct eigenvalues, you know it's got n linearly independent eigenvectors. But it doesn't need to have distinct eigenvalues. As long as it has n linearly independent eigenvectors, we still fall into case 1. Okay, so let's now talk about case 1. Let's just, let's sort of first talk about a little bit of a geometric interpretation of these eigenvalues and eigenvectors. All right, so geometric interpretation of evals and evex. So suppose we were looking at, so now the A matrix is part of a system. X dot equals AX. By the way, some of you probably saw my email just about half an hour ago. There were some, I think that problem set 5 had a few confusing of ways it was describing things. But when I refer to the dynamics matrix, or not just me, this is sort of general, if you refer to the dynamics matrix of a system, it's the matrix that multiplies the state to get x dot. So if it's a closed loop system, the dynamics matrix is A minus BK. All right? So by that dynamics matrix, we kind of mean what we call in quotes the A matrix of a system. It's not always A. It's, you know, it's maybe something else if you put it in closed loop, but it's that matrix, this matrix right here. And suppose that you started off at some initial condition, x at time 0, which was along one of the eigenvectors of A. All right, so I'm going to start on EI, where EI is an eigenvector of A. This is an eigenvector of A. And it, you know, it depends how I define my EIs, but I'll just put some scalar here, and I'll call that scalar at time 0, Ci at time 0. This is just a scalar. Okay. So now I've got an initial condition which starts on one of the eigenvectors. And I know what my solution looks like. So we know that x at time t is equal to, in general, what is x at time t? If x dot equals ax, it is e to the a t times x naught. So ci0 ei. Okay, so that's, bring the constant out front. Ci0 e to the at ei. And now let's look at that term there. We know that e to the at, in general, it's, you know, it can be represented as I plus at plus a squared t squared over 2 factorial. And I've taken e to the at and I've post-multiplied by an eigenvector of aei. All right, well, let's bring that, you know, in the infinite series, let's just bring that eigenvector in and collapse this out. Because EI is an eigenvector of A, then if I just look at that product there, so on the first term, that's just I times EI, or EI, plus AT times EI. T is a scalar, so it's T times AEI. But EI is an eigenvector, so AEI is lambda IEI. And here, if I do the same thing, this is A times t squared over 2 factorial. Bring the t squared over 2 factorial out. It's just a scalar. So this is A squared, or A times AEI. So that's A times lambda IEI, which is lambda I squared EI. Right? So I'm just bringing the fact that EI is an eigenvector in and collapsing all those A matrices down to lambda I's. Okay, so that's equal to 1 plus lambda I t plus lambda I squared t squared over 2 factorial EI. Okay, so that's just Ci0 times e to the lambda I. Okay, so if EI is an eigenvector of the matrix A corresponding to eigenvalue lambda I, then EI is an eigenvector of the matrix E to the AT corresponding to eigenvalue E to the lambda IT. And we prove that somewhat informally just using the infinite series expansion representation of E to the AT. Well, so we look at this and we say, aha, these are just scalars. So that's a fixed scalar. This is e to the lambda it, where lambda I is the eigenvalue of A corresponding to eigenvector EI. So it tells us that, you know, I've got, this is time varying, but it's still a scalar. So it says that if I start on an eigenvector, and this is my system, I'm always going to stay on that eigenvector. Suppose, actually, let's suppose here that lambda I is real. Or where am I going to say that? Eigenvector of A. Let's say just assume that the eigenvalue associated to that EI is real. Okay, so EI is a vector in Rn, and lambda I is a real number. Okay, and so now we see this is just a scalar. we also see something about, what happens if lambda I is positive. Well, let's actually sketch it out. Suppose this is my state space. The board is my state space. And here's EI. That's my vector. And I'm going to start off on, so my initial condition is some point up here. So it's some CI0 EI. That's my x at time 0. So if lambda I, the eigenvalue associated to EI, is positive, what's going to happen to the solution as time evolves? It's going to stay on the vector, good. And what will happen to its magnitude? Yeah. It'll just get bigger and bigger and bigger, right? Because you're multiplying by some scalar, which if lambda I is positive, then as t gets big, this gets very big. Right? So you'll just, you'll stay on that eigenvector, but it'll just, go off to infinity. What happens if lambda I, so same case, but now assume lambda I is negative. Suppose it's a negative real number. Then what happens to the solution? It'll go to 0. Yeah, so this is 0. Then you'll see you'll start out here and your solution will just go shh. Will it ever get to 0? No, right? Because this is a decaying exponential. So you'll start out here and your solution will get closer and, sorry, it'll stay on this line, get closer and closer and closer and closer to 0. But it'll never get there. Okay, so if you start on the eigenvector, you're going to stay on the eigenvector. And you can say something about the behavior of that solution staying on the eigenvector depending on whether lambda I is positive or negative. Now, in general, we know those eigenvalues aren't real. They could be complex. So suppose, let's just look at the complex case. So this is case A. Assume that lambda I is real. Now we'll look over here at case B. Suppose, so same setup, but now suppose lambda I is complex. And if it's complex, because A is a real matrix, we know that it appears in complex conjugate pairs. So it's going to have its complex conjugate also as an eigenvalue of A. Okay? Therefore, lambda I bar, its complex conjugate, is also an eigenvalue of A. And suppose that EI is the eigenvector associated to eigenvalue lambda I, is E vec for lambda I, then EI bar, the complex conjugate of that vector, is the eigenvector for, or associated to, I should say, lambda I bar. And that's easy to prove. All right, so what does that mean? If, let's use the notation I have in the notes. That is, so just being a little more specific, if we use the notation that lambda I is equal to sigma I plus j omega I, just being explicit about its real and imaginary components, then complex conjugate means lambda I bar is sigma I minus j omega I. And if the corresponding eigenvector to lambda I, EI, is equal to EI1 plus JEI2. Okay, so now each of these EI superscript j's is a vector in Rn. So each of these little things is a vector in Rn. The j here makes it complex, of course. Then the eigenvector associated to the complex conjugate of lambda I, or lambda I bar, is EI1 minus j. Okay. How would you show this? If I asked you to show that, you know, suppose I said, you know, A is a real matrix, it has an eigenvalue at lambda I, which is sigma I plus j omega I, and you know it's, so compute its complex conjugate of that eigenvalue. If you knew this was the eigenvector associated to lambda I, how would you show that this is the eigenvector associated to lambda I bar? You would go back to, yep.
You could write out the definition of an eigenvector, and then I believe conjugation commutes with linear operators, so that does it.
You could do that. That would be a very fast way to do it. If you didn't want to do that, you could just start at the same starting point, write out the equation for an eigenvalue eigenvector pair, and just show that if this is an eigenvalue and this is its complex conjugate pair, then this is the eigenvector associated to that eigenvalue. So I'm just going to say check that you trust this using the definition A, E, I equals lambda I, E, I, and A, E, I bar is equal to lambda I bar. Right, so just, you know, that's essentially what you're saying, but you can show it very, you can either show it directly knowing the properties of the complex conjugate and how that plays out with that linear equation, or you can just check it explicitly. Good. Okay, so now suppose, so we can't really start on an eigenvector now because we're operating in you know, Rn here. I've got my initial state, which is going to be a real vector. But these vectors are complex, so it doesn't really mean anything to start on a complex. Well, it does in some systems, but we're starting off, we have our state space, which is Rn here. So what we're going to do instead, sort of the equivalent of the real case, is we're going to assume that we start off with an initial condition which is in the span of these two eigenvectors, but it's real. Okay, so let's consider now, so we're still looking at case B here, consider some x0, which is, I'll just choose this vector here, ei1. Okay, so I've chosen ei1, and why did I do that? Just because it was sort of easy, I had it already on the board, but I also know that that's a linear combination. In fact, it's just 1/2 of ei plus ei bar. Okay, so I'm starting off with a real initial state, which I want, which is a linear combination of the two eigenvectors. And so now we just do the same thing. We know that the solution x of t is equal to e to the at x0. So that's e to the at, and I could have had a constant like I did over there. For some reason here we didn't put that in, ei1. And so now we can write ei1. Yeah, okay, so that's, well, let's do one step here, e to the at, 1/2 ei plus ei bar, bring out the 1/2. These are, you know, these are eigenvectors of the matrix A, and so you just basically do the same thing that we did over here. We just have to apply it to both ei and ei bar. Okay, so the 1/2 comes out, and then this becomes e to the lambda I t plus e to the lambda I bar t. Sorry, I forgot multiplying by ei. Plus e to the lambda I bar t ei bar. And if I plug in, you know, the actual form of what these eigenvalues look like, you can further write this as e to the sigma I t, and then I use the identity between the exponential representation and the cosine and sine representation to realize that I can write that as cosine omega I t times ei1 plus sine omega I t times ei2. Alright, where this is the real component of the eigenvectors and that's the imaginary component of the eigenvectors. So now if we have that same kind of geometric interpretation that we did for the reals, so now I've got these two vectors, let's write them, suppose they look like this. So these are two real vectors, ei1 and ei2. And so where did we start? We started on ei1. So I started on ei1 here. And so what's going to happen, I'm just going to stay in that subspace of Rn, which is basically defined by this equation here. Okay, so if sigma I, so now same kind of analysis as before. So this gives me some kind of cyclic behavior. If sigma I is positive, so if it's, so sigma I is real, right? It's this, it's the real part of the two eigenvalues that I'm looking at. So if sigma I is greater than 0, then I'm going to get a spiral which does what?
Stable.
It sort of spirals out, right? If sigma I is less than 0, I'm going to get a spiral which converges down to 0. Okay, so I don't stay on the eigenvectors anymore because that doesn't mean anything in terms of, you know, a real space because the eigenvectors are complex. But I'm going to stay in the space, the solution will stay in the space spanned by these vectors here, which are real. And the direction of the spiral, well, the direction is determined by the cosine and the sine, so it's determined by omega I. And whether it's spiraling in or spiraling out is determined by sigma I. So in this case, I chose a sigma I which was less than 0. So I got that spiraling into 0. And I chose, this is the same as the note, so I chose an omega I which was greater than 0 to get that direction of spiraling. We typically measure angles. This is the positive direction for angles.
On your notes, does it say alpha I is less than 0? Is it a typo? Is it supposed to be the sigma I?
Yeah, this should be, that is a typo. Thanks for finding that. So on page 6 of the notes, it should be sigma I is less than 0, not alpha I. Okay, so that just gives you, you know, a geometric interpretation of the eigenvalues and the eigenvectors in terms of, you know, this very simple system, time invariant dynamic system, x dot equals ax. So what have we learned here? We've reviewed eigenvalues and eigenvectors. We did a bit of pre-work on case 1, but we also just came up with some nice facts that if we start on an eigenvector, if the eigenvalue is real, eigenvector is real, we're going to stay on that. The solution will always stay on that eigenvector. And you know how it evolves on that eigenvector is determined by the eigenvalue. And the big difference between, you know, in evolution is that if lambda I is positive, you get a growing exponential. If lambda I is negative, you get a decaying exponential. In the case in which the initial condition is a linear combination of two of the two complex, or an eigenvector and its complex conjugate pair, then you get a more general interpretation that you'll stay in the space spanned by those two eigenvectors. And again, the real part of the eigenvalue of A determines whether that is a system that is spiraling in or whether it's spiraling out. And we'll see in a few lectures that, you know, that really determines the stability of the system. We'll define stability and be careful about that. Okay, so let's go back to case 1. Case 1, A has n linearly independent eigenvectors. Case 1, I'll keep reminding us, A has n linearly independent eigenvectors. Alright, so let's look at the implications of that. So we know that AEI is equal to lambda IEI for eigenvalue eigenvector pair lambda IEI. And so we also know that alright, so if we take an eigenvector and we pre-multiply by the matrix A, we get this collapse that we talked about. It's collapsing the information of A onto that scalar lambda I. Real or complex now, it doesn't matter. That's what happens. So if we take, so we know that like AE1 is lambda 1 E1, AE2 is lambda 2 E2. So in fact, I'm going to take a matrix whose columns are the eigenvectors of A. Okay, so this is a matrix whose columns are eigenvectors of A. And in case 1, since A has n linearly independent eigenvectors, what do we know immediately about that matrix? It's full rank, right? It's a full rank matrix, I can invert it. So case 1, this is an invertible matrix. But I also know from this equation up here, I've just sort of written it, I've now sort of tabulated AE1. So on the right-hand side, I can write that, I can say like AE1 is lambda 1 E1, AE2 is lambda 2 E2, and I can kind of vectorize the right-hand side as E1, so that same matrix whose columns are the eigenvectors, times a diagonal matrix whose diagonal entries are the corresponding eigenvalues. Okay, and everything up here and here is 0. All right, so I've just done n applications of that equation, and I've written it in a vector matrix form. This is invertible, and so I can immediately do a number of things. Let's just be a little, let's put a bit of notation on this. Let's call that matrix, so E1, E2, up to En. What did I call it? Use the same notation that I used last day. Let's call that matrix T. I'm going to call that T. So T is an invertible matrix, T inverse exists. And so I've got here A times T is equal to T times this diagonal matrix.
So why did we just change the name? Like, isn't it A? Isn't A that thing? Why are we calling it T?
Because A is a different matrix. This is not A. This is A.
Oh, yes.
This is a matrix whose columns are the eigenvectors of A. Okay, so it's a different thing, so I'm going to give it the name T. And I'm going to write T inverse, just for reasons that we'll see in a sec. I'm going to write it in terms of its rows. Okay, so this matrix is invertible, so call its inverse T inverse, and then compute T inverse, and now name its rows. And so the rows of the T inverse are mu1, and I'm going to use transpose, because usually when we write vectors, vectors means a vector in Rn. So this is a row vector, right? So it's a 1 by n vector. So u1 would be a 1 by n vector, and u1 transpose is that first row of T inverse. Mu2 transpose up to mu n transpose. Okay, so the E's are columns, these are rows. There's n of them. It's an n by n matrix. So it's each one is a 1 by n vector. All right, that's just notation. Okay, so now I go back to this equation here that I started with and post-multiply this equation, well, let's call it star. So we post-multiply equation star by this matrix T inverse. All right, so then we end up with A. So T times T inverse is the identity. And on the right-hand side, we have, you know, something that looks like this. Here's my matrix T. And here's my diagonal matrix. I'll stop writing zeros. And here's my T inverse written in terms of its rows. Okay, so now I look at that. So if I look at that right-hand side, I have a matrix represented in terms of its columns times a diagonal times a matrix represented in terms of its rows. And so I can rewrite that as the summation. Now I'm going to look at these individual products here from I equals 1 to n of lambda I ei mu I transpose. All right, so this thing here is interesting, right? That's a column vector times a row vector. So, you know, sometimes you've heard that called an outer product. It's fine. It's not like an inner product where it collapses to one number. This takes a 1 by n vector, it multiplies it by, an n by 1 vector, multiplies it by a 1 by n vector, and gets an n by n matrix. Okay, so this is an n by n matrix. What's its rank? 1, good. It has rank 1. What's the theorem that we think of? Why does that have rank 1? Because of whose inequality? Sylvester, good, yeah. So Sylvester tells us that that n by n matrix has rank 1. It's an n by n matrix, it's rank 1 by Sylvester. Chew. And we give it a name, we'll call it Ri. This matrix, it's sort of a special thing. When you take that sort of form, where you take an n by 1 and multiply it by a 1 by n to get an n by n matrix, that's called a dyad. Dyad. Okay, so it means that A can be written as the summation of these n terms, which is lambda, so an eigenvalue times a dyad. A equals lambda 1 R1 plus lambda 2 R2. And each of those R1s, R2s, R3s are rank 1 matrices. Okay, so this is often called the dyadic expansion of A. We see another couple of things. If we didn't have that diagonal matrix in there, and we just looked at our matrix T times our matrix T inverse. So what's T times T inverse? The identity, right? So we know that T times T inverse is equal to the identity. But that's also, in our case, that's E1, E2 up to En column matrix times matrix represented in terms of its rows, U1, U2 up to Nu row matrix. So that's also equal to the identity. Okay, so it tells us, therefore, that if we look at, the summation, we know that the summation from I equals 1 to n of Ri is also equal to the identity. Okay, so the dyadic expansion, you pull out the eigenvalues in that equation, you get the identity. Okay, let's look at the other product. So we also know that if we reverse the order here, so we'll put T inverse first. So nu1 transpose, nu2 transpose, so write T inverse first, nu n transpose in terms of its rows. Multiply by T, E1, E2 up to En. We know that's still equal to the identity because that's just T inverse times T. But now we see something that's a little more familiar. I mean, now it's just inner products, right? So now if we actually calculate what that matrix looks like, which we know is equal to the identity, but let's look at what's inside that matrix. So the 1, 1 element is, so this element here is just nu1 transpose E1. nu1 transpose E1. nu1 transpose E2. nu1 transpose En. nu2 transpose E1. nu2 transpose E2, blah, 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 all the way down to nu n transpose En. So those are inner products, right? That's just 1 by n times an n by 1 in each case. But we know it's the identity, so it tells us that all these off-diagonal elements are equal to 0 by the fact that we know that's equal to the identity. Okay, so that tells us that nu I transpose Ej is equal to 1 if I is equal to j, and it's equal to 0 otherwise. This is often what we call the, that thing is often what we call the discrete Dirac function. So it's delta ij. So that means it's 1 if I equals j and 0 otherwise. Okay, so we've looked at sort of the structure now. So we started out with the case that A has n, so case 1, A has n linearly independent eigenvectors. We formed a matrix whose columns are the eigenvectors. We know it's invertible. We took its inverse, and then we named all the rows of its inverse. So right now it's really just notation. But with that notation, we have a few other points. We can write A in terms of this expansion here, where each of these is a rank 1 matrix. But we can also write A, well, okay, so this also becomes useful for us, thinking about, like, if we look at the product T, T times T, or sorry, T inverse times T, what's the structure we get here? Okay, so that tells us now, if we go back to our original equation, we had, what did we have? Okay, so suppose we took, yeah, let's just go back to our equation here, which we called star, and let's pre-multiply. I keep wanting to use this part of the board, which I won't do. I'll go back here. So I'm going to come back to this point here, erase this, and I'm going to say pre-multiply this matrix star by our matrix, which we've called here T inverse. Okay, so now we get something, nu1 transpose, nu2 transpose, up to nu n transpose, A, E1, E2 up to En. Okay, pre-multiplying by T inverse T, that just goes to the identity, and we get the diagonal matrix here. This is probably more familiar too. This is what we call a similarity. This is called it's a very useful similarity transform. But this operation of finding an invertible matrix T and then pre-multiplying by T inverse, post-multiplying by T is called a similarity transform. This is a particular similarity transform that diagonalizes A. So here, T is, so let's actually use the correct term. Here, T inverse A T is called a similarity transform. And it's a particular similarity transform which diagonalizes the matrix So the eigenvalues, so what I have on the right-hand side here is my diagonal matrix, whose eigenvalues are the same as the eigenvalues of the matrix. A couple of other things here. We often call these vectors, eigenvectors EI. We call them the eigenvectors, but some people will call them the right eigenvectors of A. EIs are called the right eigenvectors. Okay, right in the sense of right and left, not correct eigenvectors. And why? Because you multiply them, you multiply the eigenvector on the right of A. These new i's, okay, so this over here, if we just look at that equation here, I'm just going to do another implies from that equation. I see that nu I transpose A is equal to lambda I nu I transpose. And for that reason, these nu I transposes are called the left eigenvectors. Okay. And usually these up here are just called eigenvectors, or just eigenvectors. So when we say eigenvectors, we mean right eigenvectors. Left, we have to specify.
So left eigenvectors are row vectors then?
Yeah. Yeah, you see this is a row, and then I have lambda I times a row here. Okay, so now what can we do with this? So where were we going with all of this? It's kind of nice. It's like some back to linear algebra. But now we can do a couple of things with these different expansions that we've looked at. These different, represent, so this matrix P, which we started with, whose columns are the eigenvectors of A. We've seen something that I think a lot of you have probably seen before, which is the operation of diagonalizing a matrix. So again, in case 1, if A has n linearly independent eigenvectors, you can diagonalize it to a diagonal matrix whose diagonal entries are those eigenvalues corresponding to the eigenvectors. And the reason you can do that is because this matrix exists and is invertible. So if A has strictly less than n linearly independent eigenvectors, you can't diagonalize it. This is kind of the very special case that in which you can diagonalize. Okay, so let's sort of conclude this now with a couple of interesting points based on this, these different expansions that we've done. So if you look at A squared, so let's go back to our defining point of these few lectures, which is that we're interested in computing functions of a matrix. So, now my function is the squaring, so I'm going to compute A squared. Well, I can write it now. I've got my case 1, so I've done all this, these different expansions. I know I can write A in terms of its dyadic expansion. So I'm going to write that. So that's the summation from 1 to n of lambda I e I nu I transpose. So those are my rank 1 dyads. Lambda j, that's a j, ej nu j transpose. All right, so now multiply that out. These are finite summations. All right, so we can go and manipulate them and write that as the summation from over I equals 1 to n, j equals 1 to n. I'm just writing it that way for short. Lambda I times lambda j ei times nu I transpose ej vj transpose. And I put that in brackets there because we also know something that those are these inner products that we saw over here. We know that that's equal to 0 unless I equals j. So now we can collapse that double summation into a single summation and just write that as the summation from I equals 1 to n of lambda I squared EI mu J transpose. The same dyad from A, right? But the eigenvalues are now lambda I squared. All right, so A squared has eigenvalues that are lambda squared, and it's got that same dyadic expansion. What about e to the at? That's another function of A, one that we're particularly interested in. You could just do the same dyadic expansion and show that that's the summation from I equals 1 to n of e to the lambda I t ei mu I, that should have been an I up here, mu I transpose. Again, you get that, this, collapse, that the only non-zero cases happen when j is equal to I. Okay, this holds when A has n linearly independent eigenvectors. This is really nice, right? So what we can show through this, this sort of elemental representation of a matrix in terms of its dyads, is that the eigenvalues of f of A are f of lambda I, where lambda I are the eigenvalues of A. Right? Eigenvalues of f of A are f of lambda I, where lambda I are the eigenvalues . It works for polynomials. Polynomials are always particularly easy because of the Cayley-Hamilton theorem. We're going to come back to that next. But it works for, the non-polynomial functions as well. And what's more, it's not just the eigenvalues you're pulling out, it's this very nice structure of these dyads. It says something about, how an easy way to compute these functions of a matrix A in terms of the spectrum of A, in terms of its eigenvalues, and in terms of its eigenvectors. So we're almost done here before we go to case 2. But I want to point out that just picking up on the similarity transform, why is this so nice? Why is it so nice to be able to diagonalize? Well, we've seen one reason that it's so nice here. But, if we've got, did I mess up here? 3 multiplied by t inverse. So I actually did. So, no, that's fine, t, good, sorry. No. Okay, I'm sorry. I realized just now that I defined t and t inverse opposite of what I did in my notes. So, let's just keep what we have on the board. So this matrix I actually called T inverse, and this matrix I called T in the notes. But if we persist with what we have on the board, it doesn't really matter, it's just notation. So let's persist with what we have on the board and just recognize that in the notes I've just used the inverse notation for this. So T is this matrix, T inverse is the matrix that we computed in terms of its rows, mu1 up to mu n transpose. Okay, represented in terms of its columns, represented in terms of its rows. Then we have that T inverse AT is this diagonal matrix, lambda 1, lambda 2. So I'm just kind of repeating what we have on the board over there. And we're going to give that matrix a name. I'm just going to call it capital lambda. It's a diagonal matrix whose entries are the eigenvalues lambda 1 up to lambda n. Okay, so therefore I've got that sort of opposite to the notes. That tells me that the matrix A is equal to T lambda. Let's be careful here. So A is equal to T lambda T inverse. Okay, so that's the similarity transform. So we're on page 8 of lecture notes 12, and just to translate from the board to the notes, change your t's to t inverses and your inverses. But don't actually do that, just remember that, you know, I did it backwards on the board. Okay, so this is a diagonalization. This is something nice to do. You can imagine if you're looking at, you know, let's kind of go back to our system. Let's go back to the case with input. Let's look at a time invariant linear system with input. X dot equals ax plus bu, y equals cx. Let's forget about d for now. It could go in, well, let's put it in, why not? Plus du. What we often do, so you could do a couple of things. You could say, okay, I know that the solution of this depends on e to the at. I'm going to write e to the at in terms of, I'm not going to call it a anymore, I'm going to call it t lambda t inverse. And then I'm going to use that in computing e to the at. All right, so there's sort of two things you can do now. You could, one, recall that, or let's not recall, let's just write it. E to the at is equal to e to the t lambda t inverse t. And let's actually write out what that is. So that's equal, I'm going to just do it in terms of its infinite series expansion. So that's I plus at, so that's t lambda t inverse t plus a squared t squared over 2 factorial plus t lambda t inverse t lambda t inverse. I'm going to just broach this line. Sorry, I'm just going a little bit beyond this line, but I'll say what I'm doing. Plus a squared t squared over 2 factorial plus dot dot dot. And so that's, you know, that's e to the at written in its transformed form. But then I remember that that's, well, I can just be called t times t inverse. And this can be written as t times lambda t, t inverse, plus the t inverses cancel out here, and I get t lambda squared t squared t inverse over 2 factorial dot dot dot. So that's equal to t times I plus lambda t plus lambda squared t squared over 2 factorial plus plus post multiplied by t inverse, which is t e to the lambda t inverse. Okay, so that's one reason why similarity transforms for this case 1, when A has n linearly independent eigenvectors, are good. Let's summarize what I said over here under case 1. So in addition to this nice structure of computing functions of A, I see, I'm saying the same thing I wrote here, but I'm saying it a different way. I'm saying that I can write e to the at as e to the t lambda t inverse t inverse t, which after doing that expanding into its infinite series and then contracting again, I can write as t e to the lambda t inverse. And this is a whole lot easier to compute than e to the at, right? Because how do you compute e to the lambda t? Si minus lambda. Immediately, by not even doing any math, you can, you know, compute the inverse Laplace transform because it's diagonal. You don't have to factor anything, it's all right in front of you. Okay, so this is easy to compute. So that was the first thing we could have done, or, you know, we could have done another thing. So we could have looked at that system and said, aha, I'm actually not going to even go to e to the at for now. I'm going to actually define a state transformation. Okay, so my state transformation, I'm going to define a new state z, which is equal to T inverse x.
So to verify, we're doing two different ways to calculate the matrix.
Yeah, so we're still under the case 1, when A has n linearly independent eigenvectors, and we're seeing why it's so nice to have this similarity transform that diagonalizes A. And I'm just sort of showing it to you in two different ways. One is explicitly in determining e to the at, but another is it's really doing the same thing, but it's doing it implicitly. So now I define a new state, which is, I haven't lost any information because T is an invertible matrix. So Z is equal to T inverse X. So then Z dot is equal to T inverse X dot, which is T inverse A X. X is equal to TZ plus BU, but I'm multiplying that by T inverse, so that's T inverse BU. And Y is equal to CT Y is equal to CX, X is equal to, CTZ. All right, so now I have a new system. Well, I'm going to put it in quotes, a new system whose dynamics in terms of the state variable Z are T inverse ATZ plus T inverse BU, and Y is equal to CTZ plus DU. Alright, so all I've done is I've transformed the state to a new state. What's nice about this, and now you see kind of why I did this, because now I have a new system in the state variable Z. I can always transform it back. I can do all my computations in the Z system, and then transform back to the X system through this, because I know that X is equal to TZ. And what's more, T inverse AT is my diagonal matrix. So this thing here is equal to a diagonal matrix. And so now you know the solution Z of T, you know the solution to this. So Z of T is equal to e to the lambda T, Z at time 0 plus, and then you've got, you know, the remaining terms. And this is your new B matrix, this is your new C matrix. Okay, so ability to diagonalize or to perform a similarity transform on the matrix A, you can kind of view it as simplifying your system analysis, but you're doing the same thing, but we're sort of viewing it from two different viewpoints here. All right, the first thing we did is we just said, okay, well, let's work in the X state, and let's write e to the AT, and at that point, let's use our diagonalization and show that indeed that's T times e to the lambda T inverse, or we could just define a new system. Let's rewrite our system in terms of a new state variable Z, where the dynamics in Z are particularly simple because this, what we're calling the dynamics matrix, is diagonal already. Or it's diagonal because we diagonalized it. We chose this Z particularly so that we get that the new A matrix, the new dynamics matrix, is diagonal. If you compute it, so just look at this. This is a system. It's still got input U and output Y. What's going to be the transfer function from U to Y for this system? This is the A matrix, this is the B matrix, that's the C matrix, and that's the D matrix. D's the same in this system as it was in the original. So I'm going to leave that as an exercise. Compute transfer function from U to Y for the Z system. What, even before you compute it, what does it have to be? It's got to be the same as the transfer function for the X system. And it is. Go through and calculate. It's got to be the same because U hasn't changed and Y hasn't changed. All right, so it's just a transformation of the state, but the input-output perspective cannot change. So it has to be the same, and it is the same.
Yep. Same as what?
Same as it was for the X system, which is C SI minus A inverse B plus B. we computed that before, the relationship between the. Okay, so we're done with case 1. There's a few other things in lecture notes 12 that you can go through. It's sort of based on what we just did. On Tuesday, we're going to start case 2, which is the case in which you don't have a diagonal system. You haven't got n linearly independent eigenvectors, which this T matrix depended on. And so we're going to compute the generalization of diagonalization, which is called a Jordan form representation. Again, some of you have seen that before. We're going to be treating it probably in more detail than you've seen before. And maybe take a look at lecture notes 13 before next Tuesday. I think, maybe Sylvia can give her point of view, but my feeling is that this lecture is probably one of the most conceptually new for most people in terms of interpolating polynomials and how you actually compute functions of a matrix when it's not diagonalizing. Okay, so that will be Tuesday's lecture. Good, okay, so I've got a couple of midterms. If you weren't here on Tuesday, you can come pick those up.